Okay, so today we're going to be extending what we did last time. Last time we were doing the ice tables and working with pH and so on. And then today we're going to use that idea of pH in the aqueous phase, because that's really all that we're talking about. The pH is the minus log of the hydronium ion concentration. Well, hydronium ion concentration is a water-based thing. It's water auto-ionizes into hydronium and a hydroxide. So it forms those ions. It does that. The equilibrium constant for that is 10 to the minus 7. That's where the pH of 7 comes from, and it can swing to, 0 to 10 to the minus 14, essentially. Okay, so now that we can play with the pH of the aqueous phase, if we ionize something, it'll be in the aqueous phase. If we deionize that, it'll go into the organic phase, because these are organic molecules that don't really want to be in water. There's no handle on the molecule unless it's like an OH or an acid group or something, or a BH plus, to get it into water. Once we lose those handles, we protonate it or we deionize it, then it is more comfortable in the organic phase. So we can drive things. We can use Le Chatelier's taxi to drive things into the organic phase or drive them into the aqueous phase. So that's what today's topic is. Now, this is the general idea of partitioning. So there's other kinds of partitioning. We'll get to liquid-liquid extraction, but we can take, let's say you have a polymer and you want to analyze the plasticizer. Well, you can put it in a solvent that's not going to dissolve the polymer but may dissolve the plasticizer. So that's extraction. If you wanted to get the trace metals or elements in soil or something like that, you could dissolve that. So you extract it from the matrix, and then you have your analyte separated from the matrix. So this is all about separations in some form or another. Now, digestion is even more destructive, right? It destroys the sample phase or matrix and releases the analyte. And so some of these digestion techniques are pretty aggressive and can be dangerous. So you've worked with nitric acid in lab, you've worked with hydrochloric acid. Those are pretty concentrated form. They're very aggressive. They'll burn your skin. They'll occasionally people will have their backpacks on the lab bench and they'll spill some nitric acid and it will destroy the nylon of the bag. And we've had, like straps from backpacks just get all mushy and gooey and nasty. It just starts to destroy the polymer. So we say no backpacks on the lab bench. Well, you could mix nitric acid and HCl together and make an even more aggressive acid called aqua regia. And it turns into this fuming red solution. It just looks scary. And it is scary. It'll destroy tissue. And then you can put that in a Teflon container, put your sample in there, pour in aqua regia, put it in a Teflon container and stick it in a specially designed microwave oven and just heat the snot out of it. And that will destroy like soils and things like that. So these are some pretty aggressive techniques to get the analytes out of the matrix. And that's what we mean by digestion. So acid digestion with microwave assist is a really aggressive digestion technique. And also you're heating something in a container that's going to build up pressure. And so these are special microwaves. Don't be using a household microwave for this. The doors are locked in there so they don't blow open if this thing blows up for whatever reason. So we also could use headspace and liquid to partition things. It's very simple, but when you're dumping in like gas, whole chunks of gas into a GC, the injection is not as repeatable. And so this, again, it can have some problems, but you could use internal standards to make it repeatable and correct for that injection variation. But this is a simple example. If we have ethanol in water, we heat it up. Ethanol has a higher vapor pressure than the water, and it'll go into the headspace. Then we use a gas-tight syringe to suck up that headspace. This could be done with any other kinds of volatile substance that's in a water sample. We had an example of this at West Texas A&M project that I was on, and we were testing biogases in feedlot effluent. Well, that's some nasty stuff, right? We're talking poo and pee all in a pool mixed together, and we wanted to test how many fatty acids were in there. Well, these are fatty acids. These are, oxidized products of the animal's digestion and so on. And they're all mixed into that solution. How do we get them to go into the gas phase? Well, one drop of acid, like HCl, into that solution protonated all of those fatty acids, and now they don't want to be in water anymore. So they just blow right out of the surface of that liquid, and you can smell them. And it was dramatic. We're in the lab, and we said, now if we protonate these acids, they should release and go into the headspace. And so the student had a little beaker of poo water, poo juice, and he put a drop of HCl in there, and the room was like, we got to leave. That was exactly what happened. I mean, it went right into the headspace. And so we're like, okay, this is a great technique to determine how many and types of fatty acids we have. And the ag people could kind of determine what was going on in the solution, with their ruminant experience. So this is using Raoult's law. So the partial pressure of the analyte is related to the concentration of that analyte in the solution on a mole basis. So mole fraction, we have partial pressures, and we have the vapor pressure of the pure analyte. And then we could also use Henry's law. And so if they've studied the system enough to get Henry's law constant, that takes into account any kind of non-ideal behavior. If you want to know more about this, take thermodynamics. Okay, a few of you are. Okay. So then this is valid for any of the dilute solutions. So partitioning using headspace, this is a very simple technique. And then let's get in now to water or liquid extraction. So for drugs, fat solubility is just as important as water solubility. So whenever a substance is entered into the body, it can go through the digestive tract, and there's a competition, I guess, in the body when it's distributed over the body between the aqueous region of the body, the bloodstream primarily, and then the fatty tissues of the body. And so octanol, when you hear about the water-octanol coefficient, the octanol is acting as a fat mimic. So you have the fatty layer and the octanol here, and then you have the aqueous layer, the blood layer, and is the water. And you can shake this, and then you can look at it in a GC or LC and get the concentration of the substance in each. And this is the partition coefficient. So the concentration in the octanol layer over the concentration in the water layer gives us that P. Now this is going to be concentrations. So think about your pH concentrations. Why do they have a 14 scale, 0 to 14 for pH? It's because it's log based, and the concentrations can go from 0 to 10 to the minus 14. So there's a 14 orders of magnitude in terms of their concentrations. We could have the same thing here. I don't think it's even limited to 14, but we could have an enormous range of ratios with lots and lots of decimal places in some cases, and it could be much greater than one as well. So it's good to take a log. So a lot of times we'll see log P values. So if it's a log, log P is 7, that means that the concentration in octanol is 7 orders of magnitude higher than it is in water. So that's a very fat lipophilic substance. Okay, and if the log P value is -7, that means the concentration in water is 7 orders of magnitude higher than the octanol concentrations. It's a very aqueous substance. Okay, water loving or hydrophilic. So let's look at these liquid extraction schemes. This one is trying to separate two drugs, naproxen sodium and codeine HCl. Now let me talk about the names right away. So you've seen this. You can look at the side of your medicine bottle and see naproxen sodium. So what do we know from this name? Whenever we see sodium, that's going to be in this formulation sodium cation. And so then if I want to make a neutral substance out of this, then the naproxen has to be an anion, right? So whenever you have something sodium, you're dealing with an anion, which means it's an acid. We've deprotonated that, made it an anion, and salted it out with sodium. Okay. Now what about HCl? Okay, this is right here, this piece right here is that generic BH plus, and then we have the chloride minus. So again, we're making a neutral substance. And when you see codeine HCl, you know the codeine is a base. It's been protonated and then salted out of solution with chloride and then purified and made into a medicine or a formulation. So this is telling me right away that naproxen is an acid and codeine is a base. And I don't even need to know the structures of the molecules. Okay, so that's nice. You just look at the name and you can say, okay, the naproxen sodium, that's telling me naproxen is an acid. Codeine HCl, that's telling me that codeine is a base. Okay. Here's their structures. This is naproxen, and it's an acid. See the organic acid group. Okay, and here's codeine. Okay, it's a derivative of morphine, one of the opiates. And here's the HCl. So here's the base. Do the next one. So that base right there has been protonated. Okay. So here, this is the HCl part. So they protonated the base. That's the BH plus. So this whole thing right here is B. Okay, BH plus and a Cl minus. That makes a neutral salt, and it drops out of organic solution. Well, when we get into some of the clandestine drug lab lecture, we'll talk about salting things out of organic solution. So if you have, let's say you have codeine dissolved in an ether layer, or some other, let's say hexane, something, just some bulk solvent, toluene, it doesn't matter. You've got an organic molecule in an organic phase. How do you get it out? Okay, you could bubble HCl gas in there, and it's going to make this salty substance that is not soluble in organic solvent. And so you'll start to see crystals grow. So you bubble HCl in that organic phase and you're salting out their base. And so that's a good way to get that to come out of the organic solution. Okay, so then we go to the Merck index. Remember, I brought that big old huge book last time, the Merck index. And this is some of the data that you would get from the Merck index. It has the pKa values. It has their log P values. So log P of 3.2, okay, that's telling us it's soluble in fatty substances, octanol. So P, in this case, let's just do it. P would equal to 10 to the 3.2, right? We take the natural log of that, we get 3.2. So we see it's, and P is that ratio is equal to the concentration of the analyte in octanol over the concentration of the analyte in water. So 10 to the is equal to 10 to the 3.2. So you see how that's much more fat soluble than water soluble. We can also just scoot to the right and look at the water solubility. Insoluble. Okay, but it's nice to understand if you just have log P listed that you could get that same information, and it's probably not very soluble in water, definitely soluble in octanol. These solubilities, how do we read this? These are by mass. These typically are by mass. So these are M solubilities. So this means it's 1 gram of naproxen in 25 grams of ethanol. Okay. So, I mean, that's okay. If I tried to put 2 grams in 25 grams of ethanol, it would precipitate out. That would be, so this is the saturation point. And so as long as I have, 1 to 25 or less in ethanol, it's going to all go into solution. If I get to, above 1 for every 25, then it's going to start to precipitate. Here, it's less soluble in chloroform, 1 to 15, ether, 1 to 40. On codeine, there's no data on the ether column, but there is some data on the chloroform column. And what we want to do is we're going to pick an aqueous phase, and then we're trying to pick an organic phase. So we want to pick the organic phase that has the biggest difference. We can use that to our advantage, okay? And so for to dissolve 1 gram of codeine, not the HCl, but this is the codeine, the base, we'd have to have 800 grams of chloroform. To dissolve 1 gram of naproxen in chloroform, we only need 15 grams of chloroform. So you see it's much more soluble in chloroform. The bigger the chloroform number means that's how much chloroform you need to have to get just 1 gram in solution. Whereas the chloroform on the naproxen, I only need 15 grams of chloroform, and then I can put a whole gram of naproxen in. So we'll pick chloroform for our organic layer, and then we'll adjust the pH on our aqueous layer. Any questions on this? It shows the codeine HCl is much more soluble. I think this is just for, is the 0.6 water-octanol coefficient. So that means that it's less than 1, right? So it's 6, 6 times 10 to the minus 1. And so let's look at this. This is how we decide what pH to choose. Is y'all's notes updated with this little square? No, okay. So draw this little square at the top. I was doing this on the board for years, and they were like, why don't you put that in the notes? So I'll put it in the notes. But this little square, what is this? Well, look at the x-axis is the pH scale. And maybe you want to draw this maybe on a separate page or something, back of the page or something. And so what we do is we pick the pKa's. So this is the pKa for one substance. Let's go back and look to see, make sure. The pKa for naproxen sodium. And so this is going to be naproxen. This is the codeine. And the pKa for codeine is 8.2. And this is what I call a speciation chart. It's kind of stealing a term from biology of species, right? We're trying to determine, is it a BH plus species or just B? Is it an HA species or A minus? So we're going to go through here and decide what's going on in each of these. So let's not get into those beakers yet. Let's look here. So here's naproxen. I'm gonna abbreviate that as an acid, HA, and codeine is B because it's a base. Everybody happy with that? Just a B for base, HA for acid. Which for the acid, okay. For the acid, if I've got this pKa, what's on the left side? What species is on the left side for that acid? And my choices are HA and A minus. So on the left side of pKa of 4.2, I'm going to have a species. It's going to be HA or A minus. And on the right, I'm going to have HA or A minus. Yeah. So on the left is acidic solutions. Low pH is acidic solutions. So I've got lots of protons around. How am I going to sustain an A minus when I have protons everywhere in solution? I'm not. It's going to be HA at low pH. So this is HA over here. Once I get past a pKa of 4.2, now I'm starting to get closer to a basic solution, and it's going to deprotonate that acid. That acid's going to donate its proton to water because water wants more protons. It's been stripped of 4 orders of magnitude of its protons. And so on this side, it's going to be A minus. For the whole way, like all the way up to 14, it's going to be A minus in this whole region. And so using those pKa's, that tells you which side things are on, what the species are on either side. Now before we do the base, is everybody cool with that? So acids are protonated at low pH and deprotonated at high pH. Same thing for bases, protonated versus deprotonated. Let's just use that phrase, okay? So this base at low pH is going to be protonated. What does a protonated base look like? It's BH plus. Because it has that amine group, those lone pairs. The proton's going to stick to those lone pairs, and it's going to be a BH plus at low pH. And so therefore, once we go past its pKa, we lose that proton. We're deprotonated, and it's just the neutral base. This is a great way to think about it. And you can do 15 species. It doesn't matter. You just have a row for every one of them, and you put your pKa's in there, and you could just go all the way up, and then you could see at what pH what everything is. Now, these are organic substances. So this base is not ionized. Where is it going to want to be? Aqueous or organic? It doesn't really have a handle for aqueous. Compare it to this one, BH plus. Is it going to be aqueous organic? Aqueous or organic? This right here, water loves. Water's going to love that charge. So water's going to pull that ionized substance. So this is ionized. Thanks for answering though. Ionized. Therefore, this is aqueous. So ionized and aqueous always go together. And so this one here, this A minus, that's ionized. Therefore, this is aqueous. And conversely, since these are organic molecules, the unionized one is on the organic, in the organic phase. And then this naproxen here, this is organic. So what we're wanting to do is we're wanting to pick a pH where we can separate these two molecules, one in the aqueous phase, one in the organic phase. So we have two choices, right? If we're less than 4.2, then this is what we've got. We've got a protonated base. This is the BH plus Cl, okay? And this is in the aqueous phase. But we have a protonated organic acid, that's going to be in the organic phase. So if this was a separation funnel, this would be in the water layer, and that one would be in the organic layer. And then we could, you do the little stopcock and you separate your two layers, and now we've separated the two molecules. And that's great. So we've separated one analyte from the other just using the pH and the organic solubility. What if we go above 8.2? Okay, now the base has been deprotonated. It's now unionized. It's in the organic layer. And the naproxen sodium has been deprotonated, and it's ionized, and it's in the aqueous layer. And we can see that what we've done in our speciation chart. See, if we're above 8.2, we can see base is in the organic, acid is in the aqueous. If we're below 4.2, acid is in the organic and base is in the aqueous. So we could switch them around anytime we want. Would we ever want to do anything here in the middle? If we're between 4.2 and 8.2 or whatever, then they're both in which phase? Aqueous, it's right there. Yeah, they're both in the aqueous phase at those middle pHs. We might want to do that if we wanted to separate both analytes from a bunch of other organic trash. Like if we had a bunch of other organic things that weren't drugs necessarily, but were like a polymer binder or something, how some of these capsules have a little plastic shell, something like that. It's not really your analyte. We might pick a middle pH and let all of that other junk go to the organic layer. Then we separate that aqueous layer, put it in contact with a new organic layer, change the pH either to low or high, and then we can split the analytes. So we might want to use this as a cleanup step. We start with a pH of 7. All the trash goes in the organic layer. Then we separate it, throw the organic layer away, and then put in a new organic layer into our sep funnel. And then we adjust the pH of the aqueous phase, and we drive it either this way or drive it that way, depending upon which layer we want the analyte to be in. So that's liquid-liquid extraction. It's pretty straightforward. And so this is, we put that in our separation. We can look at these water chloroform partition coefficients. We kind of have the solubility for each of these. So, for the naproxen sodium, it's going to want to be in the chloroform layer, 100%. I mean, an infinite percent. And then the codeine HCl is going to not want to be in that chloroform layer at all. Okay. We can make a general scheme. This is kind of a universal extraction scheme, which has 5 different extractions. So we would start out, we've got our substance that's been ground up and dissolved and put in this aqueous form in contact with an organic layer. We adjust it to less than 2, so we make it very acidic, extract, shake, 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 and then we split the 2 layers. So this is the 2 layers from the first extraction. You see an aqueous layer here and an organic layer here. And what's going to be in each? Well, the aqueous layer is going to have bases and things that are just naturally water soluble, like salty stuff, inorganic substances, sodium chloride, that kind of thing. Okay. And in the organic phase, the organic phase is going to have acids and neutral organic molecules. When neutrals, we mean organics. So those will be things that, are just like the little polymer coating, things like that. It's going to have the pretty strong acids because we went down to a pH of 2. Actually, no, it'll have all the acids, even the weak acids. They're all going to be protonated. They're going to be in the organic phase. So then we adjust this, we put this organic phase in contact with a new aqueous. So we bring in a new AQ phase. And we go into a new sep funnel, right? And we can extract that. We adjust the pH to 6. Okay. And so now some of the weak acids are deprotonated and they go into the aqueous phase. Okay. Let's see, is that right? This says weak acids and neutrals in the organic phase. Yeah, they're weak, so they're still protonated. So the weak acids go into the organic phase, the strong acids are staying in the aqueous phase. So we separate that aqueous here, we separate the organic there. The organic has weak acids and neutrals, so still those ones that are soluble in organic phase all the way through, no matter what we do. But we can split out our stronger organic acids. Then we put in a new aqueous phase here too, and we adjust the pH to greater than 10. We make it really basic. Okay, and so then the aqueous phase has all of our remaining weak acids because we've deprotonated all of them. In our organic phase has the neutrals, and then there's some drugs like methylbromate are still in that organic phase. So this is a way to separate the strong acids and the weak acids, and then your organic molecules with 3 extractions that go down this way, looking at the organic phase each time, a change in the pH. What about the aqueous side? Well, we get over here, now we add a new organic phase. So we've extracted the aqueous, and then we bring in new organic phase. And adjust the pH to 9 and extract. And so we're going to get In the organic phase, some weak bases and some amphoteric molecules, maybe some amino acids and things like that. The aqueous phase, we're going to add new organic phase to that and extract, and we're going to get the strong bases, strong organic bases in the organic phase, and the aqueous will have metals and other water solubles. So these things were soluble the whole time in the aqueous phase all the way down. So we can do these 5 extractions and we get 1, 2, 3, 4, 5, 6 different partitions. And this would be a pretty elaborate scheme, but this would be a way to do it. Now, in organic chemistry, we taught you how to do this, but y'all just did 1 extraction, right? Did y'all do ether solubles? What was it? It's typically what's done. Who can remember the organic lab? How many years ago was that? 2 years? Yeah. You can remember 2 years ago? Yes.
I think
It's ether was probably the ether versus water, or yeah.
yeah, because it lets them take points off if we caught the ether on fire.
Yeah, that's right. That's a good thing to take points off of. Yeah. Yeah, ether is a little tricky. It does 2 bad things. One, it forms peroxides, and so you got to use it or lose it, right? Forming peroxides in the bottle is really bad because a lot of times it forms when the ether evaporates. It's evaporating through the lid, or you pour it a bunch and you get it in the lid and the threads. It forms peroxides in there, and then they're contact or friction explosives. And so you open the bottle, and that scratchy opening of the bottle can cause it to pop. It doesn't explode like it's going to blow you through the wall, but it explodes enough to catch the whole bottle on fire. Yeah, so you go in, you pull a bottle of ether out of the flammable cabinet, boom, you got a big fire in your face. So that's bad. Ethers can be bad that way. And then also they are very, very flammable and they're heavier than air. So they creep. And so you may be working at the lab bench and they creep over here. And this is not so dangerous here at our labs because we don't have sources of ignition around. But if you're working in your garage, I have to do a little public safety announcement here, something you brought up ether. If you're working in your garage and in the corner you have a natural gas hot water heater with a pilot light, and you're refurnishing a desk or something like that, and you're using ether and it creeps across the way and hits that pilot light, it can flash back over to you. And all of a sudden the whole garage is on fire. So anyway, ether's dangerous. Chloroform's better, but it's not necessarily better for you. Okay. Now let's talk about other kinds of partitioning and separations. So we have liquid chromatography, gas chromatography, supercritical fluid chromatography, and there's different kinds of phrases or terms that we have for these. So let's look at liquid chromatography. It separates molecules by polarity, and originally we used a polar phase. So a polar stationary phase was the OG, if you will, and so that's why we call it normal phase chromatography. So that would be aluminum oxide. It's very easy to make a slurry of aluminum oxide and to get that to stick on a plate or in the tube and so on. And so that's a very polar solid substance, not soluble in any of our solvents. And so we can let our solvents drag our compounds through this aluminum oxide and it'll separate them. And then we said, well, it holds on to polar substances way too long sometimes. And so then we can make a nonpolar stationary phase and do it the other way where the nonpolar molecules stay behind and the polar ones just fly through. And so then we have reverse phase partition chromatography. So these are separating on polarity. That we could also just have a stationary phase be, for lack of a better term, sticky. So what's a sticky molecule? What if I'm coming, okay, remember, did I show you guys the red ball at Target, if that's a hydrogen nucleus? Did I do that? The hydrogen atom then goes from Navasota to Madisonville, Navasota to Livingston, and Spring to Madisonville. That's just one electron. Sodium is about as big as Texas. Okay, So how big do you think benzene is? Yeah, with that extra cloud. So benzene's a sticky molecule. It has a huge electron cloud. So if we make a polymer and we have benzene, then we have a sticky polymer. And so when molecules interact with that polymer, they stick to it. Organic molecules stick to it. So that's kind of what we're talking about, a non-polar stationary phase. We can make a polymer with lots of benzene rings on it, and then that's a sticky polymer. We could also use other kinds of substances, maybe not aluminum oxide, but maybe some other kind of uh, non-soluble thing like diatomaceous earth or something like that. Little, the little bodies of these little sea creatures. Grind them up, stick them in a column, and gases may stick to those at different rates. And so for adsorption LC, we can use a porous stationary phase. So will the molecules stick to that porous stationary phase? What if we make a porous stationary phase that has particular sizes? Then we could use that one also for size exclusion liquid chromatography. We could separate polymers. We could take a polymer and put weak acid groups on it, like sulfonates. So if we have, let's look at this one. We'll make a polymer like this. Here's our polymer. And we'll put SO3 groups on it. Then if we have a solution of cations going through, then we can have, sodium, potassium, NH4 plus moving through here, and they're all going to interact with these acid groups differently. And so they'll come out one at a time. Sodiums will come out, then potassiums will come out, then ammonium. So we can put a bunch of ions in one end of the column, run it past a bunch of cations, run it past a column that has anions on it that's stationary, and then the interactions of those cations will come out, one at a time. It'll separate them. We could also have a column of, I'm trying to think of how we do the cation columns. Are they ammoniums? Actually don't know. But we could say they are. They say they are, okay? So we'll have a NH3 plus. Now, how is it an NH3 plus? Well, it's already bonded down here to the polymer. So that's the ammonium thing, but it's protonated. And we could run chloride, some other kind of polymer, carbonate, CO3 minus, and run those through, and they're going to interact with this positive ion column, and they're going to come out one at a time. So fine-tuning the stationary phase allows us to do chromatography because things drag along that stationary phase, and they partition between the mobile phase and the stationary phase based on their chemical properties, whether it be stickiness, absorption, whether it be polarity, whether it be ion, or just getting stuck in a hole like a polymer. These polymers are dragging through, and if you got a big hole, a big polymer can get stuck in it. A little polymer doesn't get stuck, and it just bounces along. And then we could also change the mobile phase too. We could change it to make it a gas. We could also make it a supercritical fluid. So this is a fluid above its critical point. If you don't know what the critical point is, you've got to take thermodynamics, 4449. Okay. And so it's essentially a fluid that has got the mobility of a gas, but the density of a liquid. So it can fill the container. Like if this room was filled with a supercritical fluid, it wouldn't have a meniscus. It would fill the whole container. Okay. But yet it would have the density of a liquid. So high pressure gas, if you want to think of it. Then we get into the results of chromatography. If it's column chromatography, you put in all the substances at the top, and then this is that alumina packing, the Al2O3 solid, a very polar in this case. And then the analytes come out one at a time, and you have a detector, and you can see the different analytes. Thin layer chromatography, you put the dots down here, and you make a mark with a pencil, stick them in a mobile phase, and the mobile phase moves up and drags the substances along. Important, you have to mark the solvent front as soon as you pull it out of the container, because the solvent will evaporate fairly quickly and you won't see where it reached. But the nice thing about this is this retention fraction. So we put this on a scale of 0 to 1. And so this, what would you say this is, about 0.4? This is about 0.6. What do you say? 0.6 and 0.8? Would you say that? Of the way to the solvent front? And that's going to be repeatable. This is really cool because that blue mark, no matter when you stop the experiment, will always be 0.8 of the distance that the solvent traveled. And the red one will be always 0.6. So it doesn't matter how big your plate is or anything like that. They're going to go in those ratios, or the distance traveled, and come out at those fractions. But if you don't mark the solvent front, you got to redo the whole thing. So I've got a video. We did this in the workshop, the product quality cleaning workshop that we did in 2001, and we did a Sharpie marker.
Thin layer chromatography. So here we put the regular Sharpie on a slide, and here we have industrial Sharpie. And we have an elution chamber filled with ethanol. Well, it's filled. It's just got a pool of ethanol in the bottom. We're going to put that in there. And we're just going to run this experiment the whole time while we talk.
You can see the solvent already moving up.
And you guys can watch it happen in real time. Okay. You can see that ethanol line,
pretty sweet setup too.
The eluent is pushing up, and it's going to interact with that black stripe, and it's going to push those compounds up, and then we'll stop it close to the end of the lab. And you can tell that the industrial Sharpie and the regular Sharpie are fairly different. Oh yeah, let's pull the Sharpie samples off.
So immediately I pull it off
Run
and
into
make
our
a mark.
heats. So. The thing that you need to do when you pull these out is immediately mark the solvent front. So this is the industrial Sharpie. And notice I've marked the solvent front. And in chromatography, that's very similar to the retention time, is the ratio in centimeters or millimeters from this point to the solvent front. And so this dark line right here will always come out at that ratio. So it will have a ratio of about 75%. So 0.75 of that distance will be this particular substance's retention time or distance traveled in thin layer.
Now, sometimes in organic, if you do a synthesis and you've got almost no product, okay, you can put a little drop on the chromatography, thin layer chromatography, and do the elution, and you can see I've got 3 spots. I've made 3 compounds, okay? And the really good organic chemists will scrape that spot off of there and send it to the NMR or whatever. Like they'll analyze just that tiny amount that they made, and if they're really good, they can scrape it off, and then they can use that in a subsequent reaction in a micro reaction. So anyway, I don't know. Y'all were smiling. Did y'all do that? Yeah, it's pretty cool. You use a UV light sometimes. You just can't see, like you really can't even see a yellow spot. You just use a UV light and it shows up. So it's awesome stuff. Whose lab? Yeah, it's cool. There it is.
Chromatography. And likewise for this blue line, it might have a travel ratio of about 0.25. And so that number is repeatable. And so you can then describe these compounds with their travel distances, and that's a repeatable number. And this was the regular Sharpie. It's much more colorful, and it has again this blue peak is not very well retained, or is retained well by the stationary phase, and then the yellow is kind of hard to see today, but it's right there. And so
which of those compounds, the blue or the yellow? The blue was down here and the yellow was up here. Which of those compounds is more polar? Well, but think about what that stationary phase is. It's the aluminum oxide, which is super polar, and the organic phase was just ethanol, which is slightly polar. So whenever you have a normal phase, a polar stationary phase, the polar stuff is stationary. Yeah. So if the stationary phase is polar, your compounds want to be stationary and they don't move as fast. So they will come out. Think about if this was a column chromatography, how long I'd have to wait for that blue substance to come out the end of the column. Forever. If this is a gas chromatograph, and I've got a normal stationary phase, and I've got an organic acid, a very polar organic molecule, it's going to be 15, 20 minutes before it ever comes off the column. And all my other analytes come off in 3 minutes. And I got to wait 15 whole minutes. That time is money. I'm not going to wait that long for my organic acids to come off those columns. I'm going to derivatize them. I'm going to make them less polar so they move faster. They'll still separate from the others, but they're not going to sit on that column forever. This blue compound is going to sit there forever and move. And so it took this much solvent to move it 10% of the distance. So I would need 10 times more solvent to push it out the end. That's also very wasteful, especially if you're doing column chromatography, because you're just dumping gallons of solvent down and you can see your little blue line moving slowly through the column, and everything else has already come out the bottom. And it's also spreading out too, so it's getting more and more dilute, and that's a problem. That's the general elution problem.
So.
Now this is interesting here. You can take this thin layer chromatography and kind of see what we get in terms of data. So if you were to draw all of the peaks together and make a total chromatogram, you see a peak. If we were collecting data, you know, if it was coming out the end of this column, we would see these different bumps in our signal with every peak, with every substance. Now, some instruments can select an ion. Like if you have a mass spectrometer on your gas chromatograph, you can tune it to a particular ion. Let's say we knew what the blue substances were, and we picked that mass and just monitored it. We could get rid of all of these other peaks, right? So we could just see the blue signal. And so we don't see this one, we don't see this one, we don't see this one. Well, very easily, we could separate on color based on wavelength. So let's say we had a UV vis detector on there, and we tuned the wavelength to see just the blue. So only the blue signal would come through, and we could get rid of all the other crazy stuff. That's really helpful if we had a co-elution. Like, see, what if we had a little peak here and a big peak here, and the big one was blue, but this little guy was red? If we tuned our selective detector to only blue, then we wouldn't have this red signal. And it would just ignore it because it's at a different wavelength. And so being able to select the thing that your detector is interested in is a really good way to clean up your chromatograms and also focus on your analyte that you want and not all the other stuff. So an ion selective detector is the gold standard because you can pick the particular molecular weight or fragment that you're trying to monitor. It could be a UV vis spectrometer, also pretty selective. You pick a wavelength that you're interested in for your analyte. The other detectors, like just thermal conductivity, it's just got a little hot wire in there, and it's measuring the current through the wire. And if you have helium or hydrogen going past the wire, it has a certain conductivity. The electrons hate each other. So when they're going through a wire, they're going along the outside of the wire, right? Why would they be in the middle of the wire? Because they'd be closer to the other electrons. So as they're flowing through a wire, they're all around the outside. Well, what else is around the outside? The helium or the hydrogen, the carrier gas. And all of a sudden, this analyte comes puffing out of the end of the column, and it goes past that wire, and the electrons go, you know, this atmosphere is different, and so the conductivity of that wire will change slightly based upon the gas that's around it. So that's how a thermal conductivity detector works. There's lots of different detectors, but that thermal conductivity detector doesn't really give you that much about the identity of the gas. So it's not very selective. It's just going to give a signal. So it might give you this total chromatogram signal, but it's not selective. You put a UV vis on there, you put a mass spec, put an FTIR, then you can select the ions that you want to look at, or the molecules you want to look at. We can do the same thing with ion chromatography, and we can do the same thing with like liquid chromatography. Yeah, right there. So these are just different chromatographic techniques. They all have a stationary phase. They all have a mobile phase. We can fine tune the mobile phase, both in ion chromatography and liquid chromatography especially. We have multiple solvents on there and little solenoids that change the nature of the mobile phase. That helps us get those acids off the column. Let's say we're doing liquid chromatography and we don't derivatize it, and it's very polar. It gets on a polar column and it just sits there. Okay, and we've got an organic solvent going through, and we flush all the organic molecules through the stationary phase, and then when we're ready to get that acid off there, we start blending in more alcohol or something more polar. And now the polar molecules are more interested in the mobile phase. So they start spending more time in the mobile phase, and then they get drug out. But this is a really solvent programming is a great way to get liquid chromatography to fine tune the order and the speed at which the analytes come out. That right there, I'm telling you, is all like analytical chemists do. They optimize these little programs to get better separation, narrow peaks, and fast analyses. Then we have these crazy things. ELISA techniques, which everybody's familiar with now because of this, right? The little COVID tests that we did. Did anybody ever have one pop positive when you did the little swabs and put the deal in there? It's kind of a weird feeling, isn't it? You put those things in, you look at it, you're like, oh, dang. That's a pink line. I did one twice before I ever had a positive. Like I just had a cold, you know. I'm like, okay, it's negative. I'm cool. But then the one time it was positive, I put the little thing in there, folded it over, started the watch, and I saw the little solvent go past, and it was pink immediately. Oh my goodness. But these are very, very sensitive because they're using the sort of the antibody substrate interactions, which are really selective. If you think about the enzyme and the substrate, these guys are like a lock and key, a very specific lock and key. More kind of like I would say a rubber lock and a rubber key. But different kinds of keys will fit better than others, and so they can be really specific to that can be made specific to react to drugs or in this case the spike proteins on COVID or even hormones in the body. And so this is also how like pregnancy tests work. So they're testing for hormones. Now there's this blue line. Let me talk about this one here. This blue line is the control, and that's really a huge, I'd say very important. Why is a control so important in these particular setups? We have this thing here, this enzyme, and we have antibodies, which is also made of a protein of some sort. Okay. say, let me say, let me use the word I want to use, wimpy. Wimpy molecules. Why would I describe these complex enzymes and antibodies as wimpy? What are they sensitive to? Can we wreck them? Can we break them? And I'm not talking about breaking their covalent bonds. They're organic covalent bonded molecules. They're not weak that way. But enzymes and antibodies are weak in some way that we have to pay attention to. Anybody ever cook an egg? What happens when you cook an egg? It's not a trick question. Bubbles, smells good. I know, I love eggs. I eat one every day. Yeah. What else happens? You throw it in a skillet, the yolk can break. What happens eventually, though? You got it in a hot environment. What happens to it? You're denaturing the proteins. You're not breaking the covalent bonds. It's not that hot. Well, sometimes if you don't pay attention, but at first it turns clear. It goes from clear to opaque. It goes from flowy and liquidy, not quite liquid, but a gel, to a solid-ish thing, a soft solid. It's denaturing. It's a wimpy molecule. You change the temperature a little bit, and all of a sudden it doesn't flow, it doesn't function. And so these enzymes and these antibodies are subject to pH excursions. You could change the pH and wreck it. You could change the temperature and wreck it. How are we going to get these kits out to people? We're going to put them on trucks. What if that truck sits in the dock in Death Valley and it's 120 degrees outside and it's not air conditioned inside? We could wreck the enzymes. We could wreck the antibodies. And so we need that control line. The control line would tell us that that kit has gone through some experience that's wrecked the enzymes or the antibodies. So the control line is the most important thing. If that control line doesn't light up, then this kit has gone through some excursion that's denatured the proteins. And so when we see the control line, we know, okay, this kit can still operate because the proteins and enzymes and things are still in their form. And so once we see that control line, we know that the kit has got a good pedigree chemically, and then we can look to see if the other line that's actually testing the substance it's supposed to test is valid too. I love the idea that the pregnancy kit, because they'll have the control line be this way, and then the analyte line will be this way, and it'll make a positive, right? But if the hormone's not there, that line doesn't show up, and it's a negative. It's like beautiful. I mean, it's exactly what you want to know, positive or negative, right? The control line is a dash like this, and then when it shows up positive, you get a plus. I think that's very clever. Now, why do they have the electric ones? Well, because have you ever looked at one of these when it's almost, you don't have a ton of the spike protein in your body, maybe just got COVID or whatever, and you're like, is that pink or not? And so you can use a tiny little reader because it's illumination dependent. Maybe you're in a dark room or whatever, and so you can use a little reader that reads it. So it's the same kind of analysis, but there's a little electronic reader that reads the control and reads the other, and then gives you a little LED display. Now, these are very, very simple techniques, and we can automate them. And we have these plate readers where we can do these different analyses. And you've got like the 96 well, and then a 1500 well, and that goes up to 1500 well plates. This is a 384. Can you imagine pipetting into that thing? So when you get up to here, then it's robotically pipetted. You put your urine sample in there, and you got all the solvents and everything, and the robot's going over, it's like dosing all of those wells, and then you stick it in the well plate reader. Yeah. So you may be thinking, when would I be doing that for urine? Well, if you're working for the DEA or some company that does drug testing for companies, you just 1,500 urine samples come in a day, and you set up the whole system, and it does the dosing and can tell, can read those things. Becomes robotic after that. Any questions on stuff that we've talked about today? So all about partitioning. It's pretty amazing stuff.